was supposed to do this presentation in 2020, so I've had a year and a half to present, and when you know, 2 weeks ago, I'm like trying to cram new data and the most recent stuff, so hopefully everybody can pick up something on this. So I'm Dan Begle. I am the technical sales engineer for MAHLE Aftermarket. My primary focus is on working with racing, developing parts, working with production injury builders with different issues they have, manufacturing parts. So that's my responsibility with MAHLE. I realized when I put this picture, it's an old picture. I think it's a youth picture of me years ago because my hair's changed. I guess I need to update my picture. But I've been in racing for 40 plus years. I was in the NASCAR on the engine side for 27 plus seasons, and had my own engine shop for 4 years. Got a call from Robert Yates, come to work there. I worked there for 13 years, the last 9 years. They took my tools away from me, and I became the reliability engineer. So my job was to analyze engines after they race, which is really kind of cool because I spent all these years building, and your engine's only as good as it is when you're going for the checkered flag or when you're pulling that sled at the end, right? So it's what do they look like? So fast forward, I worked Jasper Engines Transmissions. I've been in automotive my entire life. So today's topic is, what is a bearing? I'm gonna scoot over here so I can read a little better. I've been fortunate. I've put in thousands of bearings in my career. I've been very blessed to be able to go to a company like MAHLE who manufactures bearings, work with engineering, work with manufacturing. So I've seen a lot of problems, and then I've been able to figure out what's going on from experience working with engineering, working with manufacturing to help bring some new solutions to the performance market. My latest venture is in the production engineering builders. But so what is a bearing? It's a hydrodynamic bearing. Is typically a low clearance assembly that relies on a film of oil and occasionally air that develops space while the spindle is rotating. The bearing transmits float, load, and a self-renewing film of lubricant. So the key word there, one of the key words is self-renewing. All right, so keep that in mind because we're always trying to feed oil in there. We're going to discuss, I have some stuff on oil bearing designs. Basically how a bearing functions is you have the shaft, crankshaft. We'll talk about rods or mains. This excludes cam bearings because they are round. There's not an eccentric on there. But basically, if you see the oil space as it's rotating, self-renewing. So it is always trying to feed oil into the bearing to create an oil wedge. All right, oil film is huge, and it's self-renewing, as we said. So it's always trying to feed that in there, which is different than a cam bearing because a cam bearing is round again, so it doesn't have that in there, which I'll show you on a slide here coming up. So when an engine fires, you have an oil pressure flow. All right, oil pressure is either a wedge or a squeeze. So in this case, the wedge, as what I was talking about, the bearing is self-renewing. So it's trying to feed oil from in a wedge. So if you think about it as if you have a door, all right, door opens and you put a door stop underneath it. The harder you push that door stop underneath, the more it wants to push up the door, which keeps the door from closing. It's the same concept with a bearing. So you're taking this much volume and you're trying to squeeze it into a smaller space, which is creating an oil pressure wedge. Now, as that engine runs, so we have engine firings, we have crankshaft flex, torsionals that happen in the crank, drag applications, clutches coming in, blowers on the front, whatever it may be. And the engine fires, it will go through a squeeze film. And at that point, it's the best way, the simplest thing is just strictly a rod bearing. When that engine fires, it's pushing down an immediate impact, which is squeezing the oil this way which allows it to go out to the sides. Okay, so keep that in mind as we go about this, as the directions of the oil as it's flowing through the bearing. So at MAHLE, we have a program when we design engine bearings. It's called the Saber Fit Analysis, and it's a software for analysis bearing reciprocating engine. It's a fancy word for Saber. There's a lot of data that goes in there to what's happening, crankshaft designs, et cetera, et cetera. So at that point, we can format this data, look at what's happening, and I have some snips that I pulled out of some of the Saber fits to kind of go through that a little more. But every bearing comes out and we make a print, all right? So it's manufactured to this print. So as we get through the analysis and kind of figure out what we need to do, there's a few things that are key, obviously. The housing bore, we give you a dimension of what that housing bore is, a min-max housing bore. And we're going to go into a little more about that as far as standoff in a further slide. So the next thing we're looking at is what's crankshaft going to be, all right? So we figure out, so we know how much clearance we're theoretically going to run. As you measure, I'm a hands person, so we do the 12 and 6 o'clock as the bearing's sitting down there, you're measuring what that clearance is, and if you rotate, you know, it gets wider. So that right there with the red arrow is the eccentricity of the bearing. All right, so that is how we form the wedge. All right, so that dimension will be so much 3/10 is an average number. We'll go with 3/10, plus minus 3 to 5, so let's say, is 3 to 5/10 larger than it is at the 12 and 6 o'clock position, as the purple arrow shows there. So that is how much eccentricity is in the bearing to create that oil wedge. So it's by design of in the bearing itself. It's nothing you change in the field. It is the way a bearing is made by design. So the next thing to point to is bore relief. All right, so you have we'll go with a connecting rod bearing. As the engine fires, a connecting rod will change its shape. We hone them perfectly round, you know, and we do make everything round, which is important. But as that engine fires, it is going to change the shape of the housing bore. All right, and keep in mind, on a typical 4-stroke engine, especially if you have a mass weight of piston rod rotating, every exhaust stroke, it's trying to throw that piston out the exhaust. All right, so when it's trying to throw a piston out the exhaust, because there's nothing stopping it, all right, that rod housing bore is closing up some. All right, depending on the rod, how good a rod you have or not is how much it's going to change. Our job to create a bearing is to create a bore relief with the orange arrow, so as that rod pinches, it doesn't disrupt the oil wedge. It just gives it a space. The other purpose of that is you need oil flow to go through the bearing, and the oil flow needs a place to go so you get enough flow to keep the bearing cool. Because if the bearing gets too hot, and we're not talking oil temperature, frictional temperature will also play in that. You need enough flow, is exactly like a radiator. You need flow to go through the radiator. If you don't have flow going through the radiator, engine gets hot. Same with a bearing. The bearing needs to have an escape that it can let enough oil out to help cool the bearing. So the oil groove. Oil grooves we engineered oil grooves, so there's some of the, you guys remember some of the 360 oil grooves, we have 180s, we have 120s. It's designed to carry enough oil to feed the rods. We're going to tie that in with the oil hole. So when we figure out a bearing, we need to calculate out oil flow. So some people, and there's been questions come up about the smaller oil hole. All right, and my first question is why? Okay, keep in mind my background is NASCAR, and to us oil flow was a big thing because it's a parasitic power loss. I have no problem with reducing oil flow. I have a concern, I should say, with reducing oil flow in the bearing, all right, because you have to calculate out how much oil is moving from that hole through the groove. Typically speaking, we want 5 meters a second, not to exceed. That number is kind of important because if you ever take an engine, and I know I know some of you guys in here, and there's different levels or not levels, but different engines and combinations, and some of this is more pertinent to specific engines. High rev engines, long run high rev engines, if you move too much oil through that groove, you actually can create your own oil cavitation, because the bearing is feeding from the main to the rod, and at that point, when the oil is moving too fast, you can create a cavitation problem by oil flow going through. So, like I said, there's a lot of talk about people trying to restrict oil. So you have to keep the bigger picture in mind rather than just choking down the oil. Okay, I have some more information on some oil flow stuff here that I think will support that from an oil flow standpoint. So on the saber fit, the other thing, when we figure out, all right, I mentioned the housing bore, which is important. When we figure out how much standoff, and I'll show you that in the next slide, but we consider in what is the material of that bearing going in. Is it cast iron, or the cap's cast iron? Is the oil pan connecting to girdle the mains? There's a lot of things going in there to affect what we have. So what we talk about is when we work on designing a bearing is how much contact pressure we want. Okay, there's a lot of discussion I get from time, not a lot, some discussion, tangs and this and that. Tangs are irrelevant to us as far as holding the bearing in place from rotation. They're a locating tang. We do not design and figure anything as far as a tang to rotate or to help keep a bearing from rotating. It is strictly a locating tang. Actually, to be honest, some of the newer applications, we don't even have tangs in there, and they just put them in there and they're centered and end of story. So when we design bearing, we have a certain amount of standoff. So if you see right there, we put a fixture and we put a stop right there on that side. Okay, at that point, we put it's on the print of a force down on the bearing. All right, so we put so many pounds with that stop in a housing bore dimension, and that creates right there the standoff of the bearing. All right, so you want enough standoff that you get enough contact pressure. When you put something together, we calculate in the material, because the material housing will actually grow too. So we calculate all that in. So there's a min-max spec, as I mentioned earlier, on the material itself, on the housing board itself. So next thing comes in, I want to increase my crush. All right, the problem that you can encounter with increasing crush by making a housing bore too small, or you may want to change oil clearance. And, well, I have this set of bearing, I don't have the oil clearance I want, so I blow out the housing bore a little bit more, and now I have the oil clearance I desire. That fixes one problem, but what you just do to the overstand? You've decreased it, so you've decreased the contact pressure, which enables that bearing to want to try to migrate as it's running. Specifically, in this group, we're at the performance show, so when you deal with performance engines, there's a lot of crank torsionals that happen. And in some applications, you can take and you can actually see the bearing will walk back and forth and you can see that it's hitting the crank. We designed a bearing for an aluminum big block Chevy. What we found is the manufacturers came in, they had created this big block Chevy, and they took everything and said, okay, we're going to make an aluminum, we're going to put a supercharger on there, and next thing you know, the bearings are walking back and forth. So go back to the drawing board, literally, and I started calculating out on the SaberFit, and the overstand was designed for a big block Chevy that was made back in whenever, and was a cast iron block. The thermal growth of aluminum is considerably more than the thermal growth on cast. So what was happening is the thermal growth was so much, it was losing the contact pressure, and the bearings were literally walking side to side. So stuff, from a machining standpoint, it's very important to kind of stay within the spec. There is plus or minus 1 bearings, and that would be the geometry is the same. It's just how much vertical clearance you get. The eccentricity is the same. So at any point you can take a standard and a -1 and intermix them, because of the bore relief allows that to work evenly and not have an issue. So it's a little hard to see. It's part of an FEA study, but oops. So if this is simulation, bore relief, no bore relief on this picture, and when you have bore relief, you can actually see as you put contact pressure in there, it's pushing out the bearing more to help relieve and I mentioned the rod bearings, I failed to mention, main bearings have bore relief also because there can be a cap misalignment. So to compensate for any cap misalignment, or if you have different materials, via an aluminum block, steel caps, there's different thermal growths. So you can actually have them changing, which is why we have to have the bore relief in there also, because we don't live in a perfect world. So a little exaggerated, some of the stuff, start-stop technology. We are working on bearings, start-stop technologies that have power adders going on there. It's a little exaggerated, but we see the amount of crank nose flex from the startup. So when that engine, you get that engine in, and it had how many, we're not even going to go into that, but how many stoplights that it stopped at and shut off, and immediately your light turns green, what happens? You're like me, you step on the gas and you go, right? The crank will have to start the motion of the camshaft and everything get going, which puts the crank in a torsional twist before the engine immediately starts up. All right, it's already torsional. Now you're spinning it, and guess what? You got to beat the guy next to you, so you're going, right? So, these are things we have to build into bearings of what's going on. It's a little hard to see this, but I just thought this was kind of cool. But I did an intensity plot of oil film thickness, and the #1 journal, you can see by the FEA the oil film thickness. As it starts moving and that crank starts to find itself its happy place again and straightening out, you can see how the oil film, it starts changing the direction of less intense, and is finally to a point of almost none, red being the most contact pressure. So you actually, when you start it, it's as worst case scenario, and as it starts running, it starts to straighten itself out, is what I'm saying. And that's relative right there to the oil film thickness. Film pressure. So film pressure is important to us also, because you can see it actually is doing the same thing. It's kind of very similar to it, but the film pressure will change as that engine's starting to run, where it's changing the oil film on the bearing itself. So more in oil flow, the connecting rod, the bearing to load and oil pressure. So in here is the 720 degrees of rotation. All right, so oil feeds the main, goes to the rod. As that engine is firing, and keep in mind the exhaust stroke. When the exhaust stroke happens, is literally trying to pull the piston rod away from the journal. So in saying that, if you look right there, you can create a point in time in that engine when you're pulling the rod bearing away from the crankshaft that you can create a negative pressure on that bearing. So your oil film is gone, your oil pressure at that specific place is negative, and it's relying on the oil galley from the main to the rod, what fluid you had in there, to fill that space up. So this, nothing you're doing, it's just hereditary of the stroke and so forth. The viscosity of oil, all that it makes it more relative or not, oil pressure more relative or not, and obviously as said, you know, that's why you're leaning to what you're understanding more what I'm saying about messing with some of the oil flow things. So I went a little old school, and this is a graph of oil flow for a 180 crank. All right, so if you look, 720 degrees of rotation. This particular one set looks like approximately 95 psi. All right, so that's the oil flow. If you just looked at the oil flow of a main bearing, what I thought was kind of interesting, and again, that was a 180 groove, just the upper half was grooved. So I dug up some information, and there is the, I'm sorry, my apologies here, back up. I said that wrong. These numbers, I'm sorry, are oil flow. That's how many milliliters a second. It's not pressure, my apologies. The 360 degree, you can see there is a considerable amount of oil flow right there. All right, so as we progress and we're getting away, and I know I've already had conversations with people this morning. It's like, hey, can we get rid of these 360 groove bearings? You know, it's like, I would love for a lot of stuff to get rid of 360 degree groove bearings, and it would be wonderful, because exactly that, between those lines is roughly 85 milliliters a second of oil difference. So you know, if you have the option, the more groove in there is obviously flowing. And you can see it up on the upper side of, as the engine picks up, through its cycles, it catches up, but is flowed so much more oil through that bearing. So this was a little fun project I had a few years ago. It took me a little bit to be able to resurrect some of this data. This is a crankshaft, a V8 Ford. And if you look, you will see there's some sensors in here, and a crank snout, and this right here, I probably had too much caffeine or it's shaky, is the wiring to come off of the front snout of the crank. So what we did is we instrumented this crankshaft to get true data as the engine was running of pressure between the main web, the main bearing in the crankshaft to the rod. So if you look, we ran 3 tests at 65, 60, and 55 psi. The top graph right there is just the pressure graph. Okay, so basically this particular engine, 7,000 to 9,000 RPMs, we ran it up there. So this here, you can see, based off that, the engine got up, it got pretty happy, it got on the PRV, pressure relief valve, and it maintained a pretty straight line of pressure for the entire run. If anybody ever studied oil pressure flows, this was pretty flat, linear. It got up and maintained. The interesting thing I found when we did this test was at 8,500, the difference, the blue line represents 65 psi, the red 60 psi, and the white 55 psi. You can see the oil pressure flow at the rod drastically changed between how much pressure you had. To me, it was mind-boggling to me to think that 10 psi would change from 8 to 36 at the rod. Go a little further, if it's a high RPM engine, keep in mind, we start out at 55 and you've dropped 44. So you're at 11 psi at that rod bearing when it's at 9,000 RPMs. It's pretty crazy. Those are actual numbers from the dyno. I had the opportunity to test that. So when we start looking at, okay, oil flow, what oil, and I tell everybody, it's like, look, when you're building an engine, you need to know what you're building that engine to before you do anything, all right? So what oil clearances do I need? Because back to some of these oil flow that I had, if you're leaking too much oil clearance at the main bearings, you've already lost. This was an efficient engine. This was a very efficient engine. Oil viscosity was I don't remember exactly. It was a thinner oil. It was around probably back then it was probably maybe a 10-30 oil-ish, I'm guessing. I can't remember. I'd have to dig that information out. But and now oils are getting thinner. It's more relative. So the more leakage you have at the main bearing, the less oil it's going to make this even worse. Okay, so it's important when you build an engine that you know, all right, I'm putting a thin oil in there, so I need a tighter clearance. You know, there's a plus and minus. You know, the rule of thumb is, you know, per inch of shaft, but you have to be, all right, I know that if I'm building this, I'm going to run thinner oil. You need to squeeze to the bottom side. If you're going to run thicker oil, okay, you can get by with here. Because what you're reading a pressure gauge, to my knowledge, I don't think there's too many graphs that actually will show you what that rod's doing, because it's hard to get those numbers as a shaft is moving at 9,000 RPMs. So it was a really neat tool to be able to look at. So bearing components, there's a lot about oil flow. So we're going to talk about bearing components. Typically, what everybody's probably more familiar with is the tri-metal. Tri-metal is exactly that. It's 3 pieces. We have a steel backing, a copper-lead substrate, and an overlay. So a bearing material, this is in reference to Clevites. H bearing is our performance bearing. Performance bearing versus a standard P bearing in our product line. We put more crush in, as we talked about earlier, so it has more pressure into it. The H bearing is a performance. The eccentricity is developed to create a better oil film, oil wedge, and just a few other things. The overlay, it's a copper tin lead overlay. So the overlay, so you start, as I mentioned before, this is, there's a steel backing, which would be down here. This is a microscopic view of it. There's a bronze substrate, and any copper tin lead will have to have a nickel layer to keep the plating from migrating into the substrate. The plating process, the natural tendency is it will plate into, so you have to create a couple micron, 3-4 micron layer of nickel, and that just creates a barrier. So the difference, and if you get into a higher performance application, we have Clevite has the V series, which is a lead indium. The lead indium it has the same bronze substrate, and it is a lead indium straight on top of it. Lead indium doesn't migrate. So the difference between the H bearing is a harder bearing, and it will give you more service life. The lead indium is a softer bearing. It doesn't give you as long a service life, okay? Saying that, the H bearing is harder, so as you have crankshaft, torsionals, flex, firing, whatever, it's harder, so it doesn't give as much. So when you get a high RPM, you have a higher power adder. The bearing is a harder bearing, so it will actually start fracturing the overlay. A lead indium allows material to move. So indium's metal characteristics allows it to move and maintain, it wants to come back to its shape. So the extreme is we do 100% of the top fuel nitro engines out there, and every one of them is a lead indium base because the amount of cylinder pressure and the material wants to stay in there. Downside is if you're going to put a lead indium in a passenger car you expect to get 100,000 miles on, it's not going to happen. All right, so you have to pick which one you want. In that application, your good street engine, you want a copper tin lead because it's going to give you a lot more service life. If you're going something and you're going to be pulling the oil pan off and you're going to be maintaining it, and you're making a lot of power, you need something that's going to last and not fracture out. So that's the big difference in the tri-metal bearings. So all the overlays, it's electroplating. I'm not going to get into that too much, but the bearing starts out with a piece of steel with bronze on it, and it's machined, and then the overlay is electroplated. So it's basically how that works. There's a tooling. You lay in a production run. This would be part of it. You put in there. It's dipped, electrodes, it electroplates it, and that's what you see. So the performance bearing, the H and the V, as we talked about the performance, they are cast bronze bearings. So if those are familiar with the Clevite bearings, if you ever get a cast bearing and you look at the back of it and it has a bluish color on that, the reason it has the bluish color is when, oops, I'm sorry, my bad. It starts out with a metal strip, and it's part of the machining process right here. It is taking copper lead at 2,000 degrees, and it's dumping it on that little strip of steel. So 2,000 degrees on steel, it blues it. It makes it blue. That's the only reason it's blue, is for that. And we're going to go into a little more of the advantages of that here in just a second. Probably not a lot of it here, but I figured I needed to at least address it. A bimetal bearing is exactly that. It's just a steel backing with an aluminum. A bimetal bearing is not plated. It is strictly a, basically they're taking a piece of metal and they're rolling foil on it, squeezing it, and at that point you're putting aluminum on it, on the top of it. Bearing is formed, machined. That's the bearing. Actually, aluminum bearing, you can still see the machine marks on there because there's no electroplating on there. So I mentioned before there's casting. Here's a little picture of it dumping the 2,000 degree copper lead mixture. It's cooled with oil, and that's what creates the bearing. Now there's another process called a sintering process. A P bearing, which would be our OEM or our standard replacement for standard engine, it would be a P bearing. It's a sintering process, and instead of it dumping this molten copper lead and cooling it, it basically takes the same copper lead, it mixes it up, and it puts it on a metal strip. It's sintered, which is basically heated, rolled, and that creates your strip. Okay. The difference, these are microscopic cross-section views. And if I did this right, yes. Okay, the difference between the two, and this is what's important to know, because you can look at all bearings, manufacturers, something like that. You look at bearings, it's like, you know, if you're like me, excuse me, if you're like me, you know, I put these bearings in and you really didn't know what you're putting in, they just worked, right? So if you put in a H or V, RH or V, it is the cast, which I just mentioned, 2,000 degrees. So the interesting thing is, these are just blown up microscopic views. These are the same materials. This is the same copper-lead mixture. All right, if you notice, so I'll go back to the melting points. Copper is the 2,000 degrees. Copper melts at like 1960. So the copper is the last thing to melt. So it's the first thing when it's cooled to solidify. All right? So the black particles are lead and copper, which makes bronze. So the steel, which is this line right here. All right, so being lead characteristically does not adhere to steel. It's kind of like soldering. Solder falls on concrete. What happens? You kick it off and it doesn't adhere to concrete. All right, the beauty of a cast is when it cools, copper will adhere to steel. So if you look right along the line right there, right along that steel line, there's a perfect layer of copper. So that's your best adhesion. All right. The next thing you look at is if you can see structural lines, support lines. So I view this as, all right, you have steel, foundation, you have if you're building a house, you have your walls and you have your roof. All right. If we're going to build a house, we're not going to put little 1x1s to support the roof. Right? You're going to put something with some support. So by cooling and making bronze, truly bronze, by melting it and cooling it, the metal characteristics by cooling will create structural strength. Unlike the sintering, which was just mixing the same components in there, and you can see this is just a random cross-section view. Steel, there is no adhesion, minimal adhesion, because it says heated and pressed. All right, there is no structure. It's just laying there. The other thing is, by doing this, this bearing here with the cast will be 20 to 30% stronger by design because you heated it, cooled it, and versus this, you just mix the exact same metals together, you heat them and smash them together. This is our P bearing. This would be the H and V. I will also note cast bearings, Cleveite is the only cast bearing out there in the market. So any other bearing would be a sintered. We have sintered bearings also. And usually when you're looking at, if you're dollar shopping, you'll notice the sintered bearings are a little less pricey than the cast bearings. Well, it's because they're easier to make, right? You just got to mix it up in a paint shaker and dump it on there and squeeze it in there. You know? But if you're looking for, and you're putting your name on the valve cover, and you're looking for reliability and your name, I highly recommend that's given reliability right there. So typically speaking, a load carrying on the cast copper, as you can see, is considerably more load carrying capacity than a sintered bearing. So surface fatigue. A lot of people get bearings in. I come to these shows and I constantly, people are pulling bearings out of their pocket and showing them to me. And I look at it and to me it's fun because it's a great conversation. I love it. But repeat overloading of the bearing causes the cracks to form. As they continue, the cracks, they can penetrate into the lining and then eventually they can lose a piece. So if you look, you watch this, there's going to be a little animation here, right in here. So this is your bearing, cross-section of it. But if you look, as you can see, there's your substrate going, cracking, 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 because it's, as you get crank torsionals or crank firing, that bearing is, I mean, a bearing is a disposable part, right? It's part of the, as the engine wears, you want the bearing to wear, not the crankshaft, because they're a lot cheaper than brand new cranks. But what happens is the propagation, crack propagation, goes down through the substrate to the point that eventually, boop, a part comes out of it. So if you ever take an engine apart, I had one this morning, guy brought me a bearing, he's like, what happened here? It's like, well, it's a centered bearing, and you had crack propagation through the substrate to the point that it connected the cracks, and a chunk of the bearing is just gone, right? So you're going through what happened to, you're trying to figure out what happened to the engine, what did I do wrong, tuning, fuel, oil, blah, blah, you know. A lot of times it's just, because when you center it, there's also porosity, there's fracture lines and centering. So you built in that problem by using a centered bearing versus a cast bearing. You have automatically said, I'm okay with that risk. So that's why I caution people doing it of, you know, get a cast bearing if it's available for that reason. So I did, it started out as just something funny I did, and it kind of had a great analogy of it. So bearings all look the same, so I had my kids make a bowl of Jello, orange Jello. So we're going to simulate this as the outer, the steel, this copper being the substrate, and then I went and I painted it. All right, so that looks great, right? It looks, you take the bearing out of the box, it looks great until you get torsionals in that bearing and the substrate starts to move. Then what happens? It's like the Jello shaking, okay? It's all fine and dandy until your Jello shakes, man. It's a bad day because this is what happens. And then we go back to the other slide, and the crack propagation comes out, you lose piece of bearings, and it becomes catastrophic. So the correct bearing, right? So the, you know, we always use this scale, all the MAHLE presentations, is getting the correct balance of what you want. I mean, you need something to wear resistance, meet your load capacity, but also we need something that's conformable. If you have a lot of crank torsions, you need something that has conformability and embeddability. So, you know, individually we can talk about what's best for your application. Generally speaking, it's like, you know, I'm trying to give you enough information you leave here with knowing a little more than when you came in is my goal. So coated bearings, I'm not going to talk a whole lot about coated bearings. Just simply from a time standpoint. But coated bearings, they add a protection in extreme hot and cold weather while reducing friction to fight against dry starts. They give long-term durability with less wear. All right, there's a whole lot more I can go into coated bearings. It's a thermal barrier. We talked about that earlier. The bearing's only as good as the lowest melting point of the overlay. So if you can create a thermal barrier that helps protect the overlay, which is what's moving, you've increased durability, you increase your reliability and durability of that bearing by a coated bearing. So there is definitely advantages of it. You know, we on MAHLE, we have two bearings, two coatings that we do. We do a C and a CT. The CT is a MAHLE-based graphite binder. The CT is a little different. It's a higher horsepower application. We only do that on V bearings because those are the high load bearings by bearing design. And the CT has indium in it, which is, if you remember I mentioned, the indium allows movement. So it allows the coating to move without causing the fatiguing that you saw. So I'm down at the bottom there, the thermal stability. that's exactly what I was referring to. You're lowering coefficient of friction, which allows the bearing to stay cooler. You get oil flow. So polymer, we're going to see it. We're going to see polymer. There's a lot of development we're doing polymer. Polymer is a lot driven on the European side. We are a German-based company, so we're heavy on the European. Polymer is lead-free. So polymer is coming, and we are evolving into that because of federal emissions or not emissions, but federal regulations saying, especially overseas, but the technology over there, we work hand in hand. So that technology comes into here. We won't have to go, oh, it's happening here in the States, which it isn't yet. But we are already preparing because it's a lot more regulated over there. So, you know, there's polymer engines out there, engines with polymer bearings that are adding power adders. So it's something we have to continue to look what's going on. You know, not only from the aftermarket performance side, we are a huge OEM supplier. So a lot of the engines you see coming, and you see these big numbers of horsepower, you know, we're having to develop those bearings with polymer. You know, there's some Dodge products out there, supercharged, you know, that are polymer bearings that we've developed. So, you know, and then you're expecting to get a lot of miles out of that. So we continue to grow with demands, basically, is saying. And the big thing you're going to hear with the ROHS, restriction of hazardous substance. That's the lingo for telling you to get the lead out of the bearings. So it's something we work with on that, and this is going to come. I mentioned that looks like anything familiar. So this stuff we're working on. Obviously, again, this is in heavy applications too, and we're looking at some of the moving forward. Some of the polymer. I am working on some of the polymer or on some of the performance applications here in the States that we can start doing. I actually have some being made right now as we speak. Actually, it probably should be about finished. An import car that people are doing power adders, basically looking at 1,000 rear wheel horsepower, and it's going to be a polymer-based engine bearing. So it is capable. I don't have fears, but we have to work through what's going on to stay ahead of what the government is saying we need to be, and not to get thrown on us as consumers to say, now what are we going to do? So polymer is it's basically a steel backing you can do on an aluminum substrate with a polymer layer. The polymer is different than a electroplating. It's actually spray applied. So it's a little more labor intensive to manufacture because you're not plating a big tray. You actually spray the polymer in there in layers to make several. It's about a micron per spray. It has the heat, and then another micron until you get to what you want. So it's interesting, but the start-stop technology is big, and working on that for future. So there's a couple different polymers that will be coming out. This particular one has by design, it is allowing it to hold oil in there, basically. For the dry starts, as mentioned earlier, with the crank flex dry starts going. So it's basically porous to a degree, and it's allowing it to hold oil, so when it starts, it has self-lubrication. So as you can see there, it basically is allowing oil to stay in there. If it gets wear, obviously it would just kind of connect some other dots and open up new oil holes. the future, more of it. Actually, it just was in a internal meeting with some other ways we're doing it, trying to get away alternative to the PTFE and going with different abilities to do polymer. As I mentioned before, you know, some of these are still, we can do them on bronze with a polymer or aluminum. So there's a lot of things going. The interesting thing is with the polymers, it becomes a slicker surface. So at first I heard that, I'm like, oh, okay, all right. But the analogy is back to that start-stop technology. I'm kind of an old school V8 guy, so it's kind of hard for me to comprehend some of this sometimes, so I'm slow. But the reduction of speed right there, 18% reduction of speed in which hydrodynamic lubrication is reached. Remember we talked about creating that oil wedge? So by the slicker surface and getting the oil to move quicker, we are managing to get it up, get the oil wedge to get a oil film 18% quicker, which is going to help heavily on start-stop technology with reliability, because every time you start 18% quicker, you're going to get that crankshaft on oil. All right, and the latest, we have a seizure resistance. We have increased seizure resistance on that. So a lot of this technology is what's going to eventually be evolving into our industry in the performance side if the government has their way and they want to take lead out of bearings. So just, you know, I guess my point to this is know that we're on top of it and we have a lot of stuff that we are working to combat this. So there's kind of just some polymer versus lead-free, PB is lead, lead-free electroplating. Some of the new technology we actually will, the numbers will dictate exactly how much wear. So this is the advancements we have made with the same application, losing 0.053 grams, which is, you know, not much. They do it in measurement of weight and versus 1 gram. So you can see the new polymers we're getting to a point where they're becoming really good. So that's why I said earlier, I have confidence as we go forward and performance is still going. If this becomes a government issue, we're a steps ahead of it. That's what I have. You know, I appreciate everybody coming. One thing I do want to mention is, if you don't mind, they would like to scan the code that's in the back of the chair in front of you, except for guys in the front. There is one in the door on the way out, just to rate the session. I feel good. Nobody threw anything at me, so I guess I did okay. But you know, with that being said, we're open the floor for any questions. If you want to talk to me personally, we're booth 1601. I'll be here all weekend, so feel free to come by and we can get however details we want to get about what you're needing. So, any questions?
On your crankshaft, where you had the instrumentation showing the pressure drop at the rods versus the oil pressure at the gauge, what was the stroke on that crankshaft, and is there a correlation between the stroke and the pressure drop?
It's a great question, absolutely. I don't have data. I only have data. You can imagine the cost of a test like that is astronomical. So I didn't get to play with different crank strokes, but the theory will tell you, theory and analytics will tell you, because you're feeding the main, you're feeding the rod, so the longer distance you have will dictate that. So a bigger stroke would be of a higher risk of losing more oil pressure than a shorter stroke.
And what was the stroke on your test one?
That one was a 3-inch, it was a relatively short stroke. That was a big bore in that round well. That was around a 3-inch 310 stroke. So that was a in today's era, that is it was a short stroke, high RPM combination. If you were building a stroker engine with a bigger stroke, I would expect to see that pressure drop even more. And I'm glad you brought that up, because I wanted to mention that in the conversation. I don't have any hard data, but if you look at how that all works, it's pressure, volume, and space. So you're creating more space. The other thing is you always have. I failed to mention also on the kind of tying it together, that void you have. There's also the plus side to a stroker engine is you get more momentum of inertia with wanting to force the oil out. All right, so there is something to gain from that, but again, I don't have any hard data. So great question. Yes?
On a piston-guided rod where you have wider tolerances between the rods on the bottom, so therefore you have more oil loss there. What do you see as far as drop? Is it increased because of that, the pressure drop?
Again, I don't have any hard data. From a bearing standpoint, though, the only bearing that is a noticeable decrease in flow would be a thrust bearing, all right? Because there you've really clamped the side up. But your side to side and moving back, whatever you run, 20 thousandths, we'll just use that number, of side to side, 10 thousandths, something, that is allows enough oil to come out to cool the bearing. The thrust can be an issue with controlling that oil. So I don't think, now there is a difference a lot of times on the flip side of that. I'm thinking as I'm saying this, so I don't have a scripted answer for that. And I build those too. Typically speaking, you're a narrower rod bearing.
Yes.
Okay, so the downside of that, a narrow rod bearing, is you have less area before it falls off. So by design of a narrower rod bearing versus a standard rod bearing, you will have more oil flow come out of that bearing just because it's quicker to the edges.
Right.
Yes.
Yeah, in this picture, it's like a 1664 bearing,
Mm-hmm.
The NASCAR style.
Mm-hmm.
You have 60 to 80 thousandths.
Yeah. Yeah. Again, if one of the slides of the squeeze film, if you start getting piston rock, because now you can control, because when I was in NASCAR, we got into that for a while. Your amount of piston rock will dictate how much load, because it's all leverage. So you can start seeing more fatigue on one side because of the firing and rocking the piston. So you can see more fatigue angle, and which, if you remember the one slide, the squeeze film, so if you're squeezing at this, you're opening up that side more, which would increase your flow. Yeah. Mm-hmm. Yes, Cass? The way we do a print is it doesn't spell that out, and it's relative to the bore itself. I know it's a very vague answer. It's relative to the area, the circumference of how much pressure you need to stand off on that bearing, and then again based off the material of the block. Kind of piggyback a little bit more, the big block Chevy, when bearings were walking, I looked at that and I did a Sabre analysis on that and did a aluminum block with steel cap and aluminum block with aluminum, and there was an overlap. The cast had this much standoff and they needed this much standoff, right? And there was an overlap, so I put that bearing right in the middle so it would cover both the cast and aluminum. I'd have to dig a little deeper to get you a better answer on that one, Cass. Yes?
I have one in regards to that chart where you're comparing bearings
Yeah, the embeddability is kind of a built-in factor via the plating that's put on there. Okay, so we figured that out. Aluminum would have a higher embeddability because it's a softer component. If you did a bimetal aluminum bearing, would be higher. But you know, aluminum has its own characteristic faults. It has a higher melting point, but it doesn't have as much strength. So you know, it's one of those things you have to look at what your embeddability from as a engine builder. You don't, it's kind of designed in on our side and how we're building the bearing with what embeddability and the thickness of the overlay that we're plating on there. So one bearing may have, say, 3/10, and this bearing may have 8/10 of plating. But that's designed in how we machine the bearing, machine the substrate before we bearing it to get the clearance we want. But that would have more embeddability per se because of the thickness of overlay before that part would disrupt.
So it's just you pick it based on the other factors and you determine it as the manufacturer.
Yeah, correct. Mm-hmm. Anybody have anything else? All right, well, everyone, I appreciate it again. I'll be down at the booth, 1601. Feel free to stop by if you want to talk about anything, and we'll go from there. Thank you very much.